Okay, I'm gonna do one more take. So, in an attempt to give some added value to the class today, I decided to make a model of the various orbits that you see our satellites in. Not just ours, but any country. And I think really more than just talking about it, visuals help a lot, and especially since satellite communications have been very important and will just get more so as time moves on. I think it's just important that everyone kind of understands what makes this stuff tick, I suppose. So, starting off, I have a few basic orbits modeled here. So I have geostationary, geosynchronous, polar, so this one here, Molniya orbits, so these out here, and one high inclination. There are a few other types of orbits. So again, you have geosynchronous, geostationary, Molniya, polar, your general inclined orbits. You have elliptical orbits of various degrees, I suppose. Inclined orbits, and you can mix and match any sort of incline or make the orbit as hyperbolic as you want, and any combinations thereof. But the orbits I have here are specific because of their traits that they help us with. Other orbits worth noting are the orbits that are held as the tundra orbits and sun-synchronous. So sun-synchronous is different from a polar orbit, as you can see with this polar orbit, it's kind of on the what's called the terminator, where light and dark meet. But as this planet moves around the star, the polar orbit will shift. So it'll spend half its day in light and half its day in dark. But a sun-synchronous orbit is tilted not at 90 degree inclination, but at 98 degrees towards prograde, which means with the rotation of the planet. So that satellites in that kind of orbit are always between the Earth and the Sun. Very helpful for mapping and or spy satellites. Sadly, I did not really feel like modeling that. I felt I could just explain it off of the polar orbits. But you can see that there. As far as other important orbits, the big ones that we use primarily, geosynchronous, geostationary, and Molniya, and the polar. So polar orbits are continuing springboarding off of that. Polar orbits are unique because they allow 100% coverage and viewing of the planet as it moves around. So, because it's always in the same place and it actually goes over the poles at a 90 degree inclination. As the planet spins, the satellites have the capability to observe 100% of the surface of the planet. I need to grab another one. So these polar satellites up there can see all of the planet as they go around. Now, because it's currently on the terminator, that's actually pretty good for a polar satellite to be at the terminator, because that means it's got 100% daylight. Maybe it's not perfect, but it helps. But again, as the planet spins and on its own axis, they can get a good look at everything. And then your standard high incline orbit. This one's circular. It doesn't have to be, again, it could be eccentric to any degree that you wish. A lot of satellites end up in these kind of orbits just because it's cheap. You can launch from anywhere at any angle. Don't really need to worry about tracking. So Depends on what you're doing. Most commonly, those are used for comms, maybe scientific, more likely. Especially if you're just monitoring weather patterns. You can put about anything, anywhere when it comes to that. But the specific, you put very specific kinds of satellites in these other specific orbits. So then we'll look at the Molniya orbit. Actually, no. We'll look at the geosynchronous first. So geosynchronous is special because as we zoom in, you can see that it hangs out over the same spot during the entire course of the planet's rotation. So because, I'm going to switch to the actual craft here, or relatively close. So the surface velocity, I should say they won't be. Geosynchronous will never have a surface velocity of 0 unless it is geostationary. And that's, again, a very, very specific type. But geosynchronous, they maintain this, but that velocity change that you're seeing here occurs from its movement up and down. Now, if it's at a high degree of inclination, like a polar orbit, but it's a little off, that movement's east to west, not up and down, north to south. So, but again, it is always, like you can see right there, it's always hanging out generally over the same area, which is good. So now this only has a problem in terms of communications because as it moves north and south, maybe it's covering different latitudes, and you might fall out of connection unless it's using a relay. So back to the tracking station. So then the king of that is a specific type of orbit. It does have a surface velocity and geostationary. They have an orbital period of 1 sidereal day. So this doesn't move at all. So it's moving at a constant velocity in space and 0 velocity in relation to the surface. So it doesn't move at all. Geostationary is always at a 0 degree inclination relative to the equator. That is just a fact. So they do not move, not at all. It's just a nice, happy line. But again, they will maintain their position throughout the day. So now that is a problem when you're trying to the Molniya orbit. So the Molniya orbit is a bit different. So now this one's on the northern side. What it does is it spends a lot of time up on the up over its target area, and then it just zips around super fast to the bottom or top of the planet. It's apoapsis, or sorry, periapsis. It's, it moves very, very quickly. There it is. So it spends a lot of time at the apoapsis, so very far out, and then it gets real close using gravity, and it swings down and doesn't spend very much time out of position. So the Molniya orbit was picked because, of course, most of Russia is at a very high latitude. It's also very easy for them to launch and put them in a position where it's easy to monitor us as well. So that's worth pointing out. But the geostationary doesn't help that much. Stuff really works out when you start using it in the cluster, so these green lines represent connections between all these different relays. Let's look at the southern Molniya. It's got a little more daylight. 3 degrees, 60 thereabouts. Again, they have a orbital period of 1 day. So again, very, very fast around the far side of what they're supposed to be watching, so, you know, we hang out down above generally the same area, and we move real fast. So, like, let's watch the speed here. We slow down. At our slowest, we're around 500 meters per second, and at our fastest, we're almost hitting 3,000. That would be much faster. This system is only 1/10 scale, so all the speeds are meters per second, but that creates large floating point numbers, and that's hard to model. So yeah, the Millennium orbit's designed to just kind of like watch out on the extreme polar regions or just very high latitudes. So I'm going to make this go a little bit faster. So the thing about geostationary and geosynchronous, and it's worth pointing this out, notice they're all perfectly stationary relative to each other. Now, the geosynchronous are moving up and down, yes, but their orbital period is the same, so they're not catching up to each other. They're not, like, the geosynchronous aren't catching up to the geostationary. They both have an orbital period of 1 day. Now, I mentioned earlier the Tundra orbit. The Tundra orbit's very like the Millennia orbit, where it's at these high angles, you know, usually 63 degrees or thereabouts, but they are different from the Millennia orbit, where the Millennia orbit's only half a day. Tundra orbits are 1 full day. The problem is you can't get nearly as much useful time from when they're at the apoapsis or the apogee, you know, hanging out at the top of their curve. So now most of these satellite systems are launched in clusters, is what they're usually called, a cluster or constellation of 3. So my geosynchronous and geostationary are in 3s. My polars are in 3, except they've gotten a little out of position because I didn't perfectly align those. Millennias are also done in groups of 3. Now, those groupings don't have to be on the same orbital path. They can be slightly off when you're using a Millennia orbit. But geostationary, geosynchronous need to be 1/3 orbital period apart from each other. So, and in general, if you're going to leave them on the same orbital path, you can do that with all of them. But hopefully the visuals helped. If you have any questions about how they're put in those orbits, why we put those in those various orbits, feel free to just ask me. But again, hopefully I've helped. Thank you.